Alright, we're going to finish up with our discussion on friction with one real massive example. So this is going to combine everything that we learned. So there's a lot of little traps in here, so this is one we've got to be really careful with. So I'm going to throw myself into the example. So I'm going to drag a box full of physics exams up a steep hill. Why I would do that? Who knows? So it makes this hill, and I've chosen a really good one. I've chosen a hill with an angle of 40 degrees relative to the ground. So this box, it's 100 kilograms. Assessments aren't light. So the coefficient of friction between the box and the hill is 0.750, and I can accelerate at a nice little pace of 0.150 meters per second squared up the hill. So we want to determine the applied force that I have to apply in order to get this box to go up. So here's kind of what's going on. Once again, let's make a nice little sketch. We'll make our 40 degrees. So we got our 40-degree angle. So we have this box of physics exams. We have myself pushing on this up. And then, you know, I'm a little upset about this. So I'm going to throw that in there. So that's kind of what's going on in here. So the first thing we want to do is we want to draw a free body diagram. So in this example, there is a lot going on. But we can always draw, for anything on an inclined plane, we can always knock out our first two. The two that are always going to be there. So we got that force of gravity that is going down, and we are going to have that normal force that is perpendicular to the plane. So those are our two freebies. Now we have to start to factor in a few things, or a few other things. So first off, I'm pushing this box up the plane. We have to have an applied force up the plane. This is what we are interested in. So we're going to have this applied force that's going up the plane. And we're also told there's a coefficient of friction. It doesn't tell us it's kinetic friction, but we can kind of know that by context. So there is a force of kinetic friction. We know that friction is going to oppose our motion. So if I'm moving up the plane, the force of kinetic friction has to be opposing the motion, so it has to be going down the plane. And then last thing we can do, we can break up our vector here for the force of gravity. We can break it up into its components. We have this component that's perpendicular to the plane. And we also have this component that's parallel with the plane. So we have, not counting FG, since we've resolved it into its components, we have 5 forces that we have to deal with. So a lot's going on here. We have to be really careful with this one. Before we get to it, let's set a positive convention. So since the motion's going up the plane, I might as well call up the plane positive, and perpendicular to that plane, we're also going to call that positive. Now, with everything in terms of forces and planes and all that, we're going to start parallel with the plane. So parallel to the plane, let's see what we got going on. So parallel to the plane, the net force parallel to the plane. So we have 3 forces we've got to deal with. We have this applied force, we have this force of kinetic friction, and we have that one that people like to forget a lot. Don't forget, parallel to the plane, we also have that component of the force of gravity that is parallel to the plane. So we have this applied force, plus this force of kinetic friction, plus this force of gravity parallel with the plane. Now in this case, the object's moving. We're told its acceleration, so we know F net is going to be ma. Fa is what we're looking for. The force of kinetic friction, I'm going to leave this alone for a second. And the force of gravity, we have this, or this force of gravity parallel, we have this mg sine theta. Now you might say, well, Mr. O'Donnell, we know the force of kinetic friction. We know it's mu k Fn. You're right. I want to hold off on that for just a bit, because as I mentioned in the previous video, using Ff equals mu Fn, it's a great equation, but it also doesn't give us much info on direction and signage, so we have to apply that really carefully. I'm going to come back to that one. So we know in this, the objective is to find Fa. So if I rearrange this, Fa is going to be this ma minus this ffk minus mg sine of theta. So this is a pretty big equation. What do we know in here? We know the mass, we know the acceleration. In terms of the force of kinetic friction, we know the coefficient of friction. We don't know the normal force. So this one we don't know. We know mg and we know sine of theta. So we can't solve for the applied force just yet. This is again where we have to go to this. This is where we have to start going perpendicular to the plane, because we've kind of hit a dead end parallel to the plane right now. So let's look perpendicular to the plane. So perpendicular to the plane, I have this normal force that's perpendicular to the plane, and I also have in this same plane here, I have this force of gravity parallel. So the net force perpendicular to the plane surface, we have this normal force plus this perpendicular component of the force of gravity. Now, regardless of what we're doing on an inclined plane, this box of exams that I'm pushing up, it's not just going to start to spontaneously move perpendicular to the plane, like it's not going to just skyrocket up perpendicular to the plane. So we're going to say that the net force perpendicular to the plane is 0. As I mentioned with inclined plane problems, pretty much all of them, that's going to be the case. So we're going to get this 0 is equal to Fn plus Fg perpendicular. So the normal force is going to be the negative of the perpendicular component of the force of gravity. We're going to have this negative mg cos theta. So I could plug in all these values. So I know I have this negative, so I have this mass, it's 100 kilos. Now, gravity, I'm calling up the plane positive, and I'm calling up. Basically, all of these upwards directions are acting as positive, and perpendicular to the plane, I'm calling up positive. With gravity going down, we're going to have to put that in as a negative. And then we have cos of 40 degrees. So this is going to come out as a positive number. That's good. Based on our convention, we should expect the normal force to come out as a positive. So what I'm going to get here is I'm going to get about 751.49 newtons. I'm not too worried about significant digits in that for the moment. So this is going to give me my normal force. And this gives me the appropriate signage for the direction. Because we said based on our convention up here, perpendicular to the plane is positive. The normal force is upwards perpendicular to the plane, and we did get a positive. It's going to be calculating the force of friction where we have to be careful. So we're actually going to determine that separately. So we're going to determine specifically the magnitude of the force of friction. So we know our equation for the force of friction. It's, in this case, it's kinetic. It's going to be the coefficient of friction multiplied by the magnitude of Fn. So neither of these cares about direction. So we're going to have that coefficient of friction, that's 0.750, and then we're going to multiply that by our Fn that we just calculated using the perpendicular component of gravity. So we're going to get about 563.62 newtons. Again, we're not worrying about significant digits for now. Here's where the issue comes in. This is always going to give us a positive number because we're dealing with magnitudes. This is one of those cases where you have to be mindful of sign conventions and really pay close attention to your free body diagram. So if I go to my free body diagram for a second, we notice that FFK is pointing down the plane. It's pointing down the plane, and we've called up the plane positive. What that means is if we want to actually take direction into consideration, this has to be a negative number. So this must be a negative number to respect sign convention. So when we put this in, FFK, we're actually going to say it's negative 563.62 newtons. Because that negative there is telling us that this is acting down the plane. And that's the, well, I won't say it's the only thing, but that's definitely one of the major pitfalls of using FF equals mu Fn. It's necessary in the course, but when you're using that equation, you have to take that extra step to be extremely mindful of direction. So be really careful with that. So now that we know FFK, we can plug that into here. So this is going to be a big equation. So let's plug in what we know. So my applied force is going to be the mass times the acceleration. And then I have to subtract off my value of the force of kinetic friction. But that's where we're going to put in that negative. And then we have this 563.62 newtons. Again, we're going to use our unrounded value here. And then from that, we're going to subtract off, once again, the mass. Now, we have called up the plane positive. The force of gravity parallel is going to act down the plane, so G has to be negative 9.81 meters per second squared here. And then we're going to have sine of 40 degrees. So this is a fairly long equation. There's a lot of terms, a lot of places we could make mistakes, but definitely the two biggest mistakes we could make in here, not having the negative on FFK and forgetting the negative on G. So as I've tried to emphasize over and over and over again, you have to, a well-drawn free body diagram will help you a lot, but you also have to be really careful with your signs. So if I do all this, I'm really careful with my math, I'm going to get about 1,209 newtons. Now for this, we're going to put this into 3 significant digits. So I'm going to say that the applied force is about 1.21 times 10 to the 3 newtons. But it didn't say magnitude of the applied force. So this means I have to have a direction. Well, I said the acceleration's uphill. Uphill is going to work just fine. We could say uphill or up the plane for the direction. That's more than sufficient. If you want to say 1.21 kilonewtons up the plane, also works. But this is a type of question where we throw everything at you. If you can handle something like this, there's not a lot with frictions and inclined planes that we can give you that you can't handle. But my big caution in this, be really careful with the sign of the force of friction when you're using mu KFN. If you're really mindful of sign conventions and you drew a good free body diagram, you shouldn't run into any major issues.